Yeah. Hi, everybody. My name is Rahul Singh. I'm with the Anant Corporation. My role at this firm is primarily as a platform architect around real-time platforms. We work with Cassandra, Spark, Kafka with customers. We're partnered with DataStax. Also have a little bit of a partnership with Confluent. They make Kafka. Today's topic is about migrating from relational to Cassandra. Many of the concepts here really you can apply to any NoSQL system, but this particular talk is how to think strategically when migrating an application that is built on a relational system. When we move it to Cassandra, why would we do that in the first place? So we're going to cover the why. Why would we want to do this? We're going to cover a little bit of what is it that we need to be thinking about, and we'll talk about how at a strategic level. I'll give you some pointers in the more in-depth how, the tactical hows. But hopefully by the end of this session, you'll be able to walk away by, even if you've never heard about Cassandra before, you should be able to walk away with a basic understanding of what are the differences. Why do those differences matter for applications? You know, what benefit does Cassandra bring to the table? When people do move to Cassandra, how do they do it, and how are they successful? Right. And then finally, one aspect of it is about how to detect issues. Well, sometimes when people migrate to Cassandra the wrong way, their issues arise, so how to detect those issues. Just a quick review of the table of contents or agenda for today. We're going to look at core concepts, data modeling in Cassandra, a bit about synthetic sharding, key design, and how to avoid tombstones. Those are the major reasons why migration projects fail. And you know, when we are moving to Cassandra, what are the common patterns? As I mentioned earlier, we at Anant, we build real-time business platforms connecting customer experiences with information systems with real-time data and analytics, platforms like Cassandra, Kafka, and Spark. What does it mean to be a platform architect? Well, we are thinking about the whole company. How does some application integrate with the whole company, the customers, to the employees, to the things, to the APIs? Sometimes it means to work with various different tools out there. And that's just the way business is today. People use software as a service, cloud software, on-premise data centers. But the way we challenge ourselves is that it's not about the technology. It's really about what the goal is for end users. And end users, they just want something that works. They want a platform where they can use it on their phone, they can use it on their browser. And the technology that we use are meant for big scale. So Cassandra is one of those tools, core components that can really scale at a global level. Many times what people do, and where we help them, is we help them get their information streamlined into processes, get it organized into some sort of a data lake, and then eventually it's unified into views that people can actually use. Now, what's happening is, as a trend in the last 5 years, we've seen is that people want this all in real time. Any update in one part of the company, they wanted to see it in the other part of the company. We've helped various clients with Cassandra and with DataStax, amongst other tools. With our partnership with DataStax, we've been able to really make an impact on some of the larger organizations. And we continue to work with smaller DataStax customers as well. What are the differences between relational world and Cassandra? Well, let's talk about what do people use relational databases for anyways, right? Let's just do a quick review. And I'm not going to exhaust the full list of what relational databases are used for, but it is good to kind of remember, you know, when we first started working with relational database, what did we encounter? So I encountered a bunch of master detail systems, right? Orders that have order details or order items. We had document attributes, meaning we had an object, it had another extension object, and they just had a one-to-one relationship. Or there was a lookup table where, you know, one foreign key in one table was really just related to a string in another table as a lookup value. And that was all part of the, you know, normalization process. Or things had connections. We had relationship tables that all they did was connect different objects, right? And this worked. I think it still works pretty well in some cases. So why do we want to look at Cassandra? Well, amongst the other NoSQL systems out there, let's talk about why even NoSQL in the first place. Well, NoSQL was created, non-relational databases were created to basically scale to the size of Google or Facebook or Amazon. Because the amount of data that was being written to and read could not be managed in the way that a traditional relational database is managed. In a traditional relational database, because of the ACID compliance, immediate consistency, tables would lock when you're trying to write two columns on a particular table at the same time, or if you're trying to read it, it wouldn't let you read it unless the write was committed. That's one aspect of it, but then just by design, a relational database is monolithic. It is meant to have everything in one system. And scaling it, and we'll talk about that in a second, scaling relational databases is it's very cumbersome. Although some people are professionals at it, when compared to the way we look at Cassandra, and you'll learn more about why Cassandra is a little bit more simpler to scale. But you could talk about relational to non-relational with many different types of databases, Cassandra being one of them. But why Cassandra? Well, it has a familiar structure. You know, CQL tables, Cassandra Query Language tables, they look and feel like SQL tables. So if you're coming from Oracle or SQL Server, you can look at a schema declaration and know what it is, right? A familiar query language. So in addition to the data definition language being similar, the data modification language, DML, is also very similar. Right? It's not the same, but it's similar. So major difference, that you have to get used to is that you're not going to have arbitrary queries. I mean, there are extension tools like in DataStax, there's DSC search, but in core Cassandra, there aren't any arbitrary queries. And for every query that you want to do, you basically have to make a table, or you have to define an index or do a materialized view, and those have costs associated with it. We'll talk about, well, what does that cost mean? Why should we have that cost or not? But a big thing is that you have to think differently about transactions. There are transactions in Cassandra because it has tunable consistency, but it's not the same type of transactions that you see elsewhere in the relational world, where you can have related tables as part of a transaction, right? And the big thing is that there aren't any inherent joins. Of course, if you have DSC analytics, you can do Spark SQL, and it can join. And if you do DSC search plus DSC analytics, it can do joins very efficiently. But why Cassandra? Well, in our experience, it's the easiest big data database to get started with. And once you start using it and start to use it the right way, you can truly make globally scalable software. And the people that use Cassandra, and I'm not going to name any companies, but every major brand you use has Cassandra powering some major part of the platform, the user experience. And that's ultimately one of the main reasons why people use Cassandra. It can scale the data needs for millions of users around the world and have that data consistent across physical boundaries. The other is that it's super fast for writing and reading. Super fast and super consistent, eventually consistent, but very, very quickly it can move information across the world. So it's like if you wanted to build your next generation cloud platform and you had a choice between MySQL or SQL Server or Oracle and do master-slave architecture or use Cassandra, you'd probably use Cassandra because of the way it's architected. I'm not going to go too much into the methodology. This is really the realm of DS220, which is a free course available on DataStax Academy, which talks about how to go from a conceptual data model and an entity relational diagram to an application workflow, which is how somebody uses the system, is how the design of the Cassandra database is dictated. And then finally, there's some tools, Shabbat code diagramming tools. It's just a notation, basically, to help you design it. So we're not going to do that. We're not going to do a basic Cassandra data modeling exercise. That's part of DS220. That's freely available on academy.datastax.com. What we are going to do is we're going to assume that you know how to do this, and we're going to think a little bit larger and say, okay, how do we do it the right way? We did actually just talk about a few of the differences, but you know, major differences are, well, in a relational world, we try to reduce redundancy. In an unrelational Cassandra world, you can store that information as often as you want. Disk space is cheap, right? Duplicate it as needed. In relational, we store once, we relate and we query. In Cassandra, we have predefined queries, and that's how we store data. I liken it to, I'd actually refer to it later, if you were to design your Cassandra tables as if you were designing a REST API, you will not have any problems. And that's actually part of today's talk, is how to think about your APIs so they work well in Cassandra. When we talk about tunable consistency versus immediate consistency, what we're really saying is if you want to know if a particular record has been written to on all the replicas, you can tell Cassandra, hey, make sure, you know, consistency level all. Make sure it's every node that could possibly have this copy acknowledges that it has the copy. Or you could say, you know what, just let, even if there's 3 replicas of this data, just let me know if the first one says, yes, I got it. Other major differences are really about the master-slave limited scale versus, you know, masterless or multi-master, and what we can do as a global cluster, multi-DC. Multi-DC means you can have US East with one data center, US West with one data center, and have the same key space replicated on both, and have APIs writing to and reading to from both data centers. And all of that data will be eventually consistent. There's no master at the data center level or at the cluster level. And that's why it's globally scalable. Core concepts related to what we were just talking about, right? Why would you really, really need Cassandra? Well, it's not for tiny data. It's not for gigabytes of data, right? It's maybe not even terabytes of data. It's closer to terabytes of data that is being written to and read all the time. Okay, if you just want to store terabytes of data and not look at it, you could just put it into HDFS or S3 and just let it sit there, right? Main thing is that it needs to be It can be transactional. Do we want the data to be available all around the world? May not be today, but maybe in the future. In fact, some of the customers we talk to, they only have information in one data center, but it's in their plan to expand their platform to be in multiple data centers. Maybe going from US East to US West, and then maybe Singapore. How can they keep all of their data consistent? And then obviously they don't want the system ever to go down. And so disaster recovery in Cassandra is really about disaster avoidance. How do you design a system that never goes down? Never goes down because of acts of nature. It doesn't go down because of human error. It doesn't go, well, human error can bring down anything. I'll take that back. It doesn't go down if Amazon goes down, right? You can design a very fault tolerant system with Cassandra. And because it's open source, you can have it on Amazon and Azure and in your own data center. It doesn't all have to be in one data center. One cluster can span all those different places. Quick thing about access pattern, access. When you have a application that's accessing Cassandra cluster, it can talk to any of the nodes, right? There's no masters. And whatever node it's talking to, it is referred to as a coordinator. If that coordinator does not have data, it's okay. It'll go to the right place and get it. Now the magic is that if you have the good drivers, DataStax drivers are really good, then even before you insert the data from the client will know which node to send the data to. Even before you retrieve the data, right? If you know the primary key, it will know which servers to get it from. And that magic is because of the partitioner, and that's an advanced topic, but that's one of the main reasons why Cassandra is so fast. Because as a fault-tolerant system, any system accessing it has the same partitioner as Cassandra itself. So it's able to just go to the right place and get it. And that basically removes the need for having a master node or a name node as you have in HBase. How's data stored in Cassandra? Well, it's a key value store. Under the hood, it's n-dimensional database. But we look at it like as a two-dimensional table. Right? So you can have a schema in which you've only set the value for 3 of the columns. And you can have another row where you've only set it for 2 of the columns. It doesn't store what it doesn't have. So that means you could have 1,000 columns in the schema, but only use 4 or 5 of them for some rows and 4 or 5 other ones for other rows. So we'll come back to that idea in a second, but that allows you to store a variety of information in one schema if you want it. Why would you do that? Well, sometimes lookup tables don't need to have, 5-row lookup table does not need to have its own table in Cassandra. That's a waste of resources, right? Those are the type of things that you could actually just put into all of your lookup tables. You could put into one table. We'll talk about that pattern as well. But you can't get data from Cassandra unless you have the partition key. If you don't have the partition key, you cannot get that information. Unless you have a secondary index or a materialized view or a Lucene-backed index like DSC search. But that has a cost to it. Every time you make a secondary index, you're basically making another table under the hood. And sometimes if your design of your key isn't good, on which you did that index, you're going to have skew, and we'll talk about skew in a second. A cluster is a collection of key spaces. A key space is a collection of column families or tables. They're interchangeable. Newer versions of Cassandra, we call them tables. Tables have rows. Rows have columns and values. But at the core, it's all key value. Everything is stored as key values. Not going to go too deep into read and write path, but this is here for just reference. You can always come back to it. Data comes into Cassandra, and the reason it's available immediately is because it first gets put into a mem table. Well, it gets put into commit log, but it gets put into the mem table. So the moment you write it, you can then get it. And over time, it flushes it into something called SS tables. And how we manage SS tables, that's another topic of, what is the best practice for if it's read heavy or write heavy. We can go deeper into that later. On the read path, it's a little bit more complicated, but it basically has to go to a partition cache or a row cache. If it doesn't, it goes to your mem table. If it's in the mem table, it gets it. Otherwise, it eventually has to go down to the SS table itself. And there may be many different SS tables, and it has to look into the partition index. There's a thing called a Bloom filter, which allows it to be fairly efficient in figuring out which SS table to go to. But these are the nitty-gritties. I would say that if you've used SQL Server or Oracle and you're an advanced user, you have learned the read and write paths, and your fundamentals that you know there are going to help you if you want to become an advanced Cassandra DBA, because ultimately it's all about disk, memory, CPU, right? And Cassandra's fast because of the way it deals with writes and reads. Why is it so fast? It's fast because every update is an append to the commit log and an append to the SS table. It does not go seek the original value and then update it. It just writes it. And then on the merge operation, when you read it, that's merged into your most current copy. And that's why we can scale it to billions of operations or trillions of operations per second across hundreds of nodes, and not have an issue with locking or finding where that information is. Cassandra can have some major issues. There's another talk that I've given. It's called Common Data Modeling Problems in Cassandra. You can Google it. And we're not going to give that talk today, but what I'm going to show you is how bad design can end up with problems. We've written a tool called Cassandra Vision, which we will open source soon, but this visualization is actually from that tool. And what we're seeing here is one of the major problems, one of the three stooges, I would like to say, in Cassandra, if you don't design properly, are wide partitions. And a wide partition basically is a partition with either billions of rows or with billions of columns. It doesn't really matter what. That's just a visualization of it, but it's just a fat partition. And it's problematic because when we do a read, it has to pull that partition into memory. And if you are looking at this carefully, this is a 4 GB partition. Basically, it's 4 GB of data that even if you needed one row, it has to always pick up 4 GB of data. Now, you may say, well, why couldn't you put an index on it? Or why would you need to pull up the whole thing? Well, part of the reason why Cassandra is very resilient and can spread and can distribute data is that a partition is the most fundamental unit of replication. So when we say write data here and we're going to have 3 replicas, any change to a partition on one machine has to be replicated on the other 2 machines. And whenever we do a repair process, each partition is then made identical across the 3 nodes. Why? Because if one node goes down, those other 2 are then the definitive copy. Or if 2 nodes go down, at one partition is a definitive copy. So a partition is fundamental part of Cassandra. And if they're huge, it's bad news. We'll talk about how to avoid them. Data skew. Data skew comes from bad key design or inconsistent traffic. And what we're seeing here is that there are only 3 out of the 9 machines that have data here. Or here, 2 or 3 of the nodes have more data saved than others. Why would that happen? Well, in this case, because we only have 2 keys and no more, the only data that's stored in this table is really on 2 partitions across 3 computers. Across 3 computers because it's been replicated 3 times. And in this case, it may be because some data is more popular than others. So what I mean by popularity, if you have a key that's accumulating a lot of information because data is getting written to it more, that's going to cause some skew. Another one is tombstones. Tombstones are how Cassandra deals with deleting data fast, right? We just talked about how everything in Cassandra is an append. Well, a delete is also an append. It's just a marker that says delete this column or delete this row. And up until it's actually deleted through a garbage collection compaction process, it is just part of that ledger that needs to be merged, right? So if you do a bunch of reads and writes and a bunch of deletes, all of those little operations, if they're not compacted, they have to be merged in memory. And that's why, because there are so many tombstones here, latency for this table, read latency is very, very high. So designing Cassandra tables, we have to keep in mind some very basic fundamental things, and if we keep those in mind, we won't run into these problems. But I will talk a little bit about how to detect these issues. Even if you don't have Cassandra Vision today, you can still do it with other tools. Right? So you can use CF stats or table stats today, where you can look for bad key design. You can just see how many keys are on a particular table across all the nodes. Or just see how much of the space used is spread across all the different nodes, right? You can monitor it using DataStax Op Center, Prometheus and Grafana. In fact, the later versions of DataStax have a commercially supported Prometheus exporter that will send data to a Prometheus server, and then you can visualize it with Grafana. Datadog, Semitext, or some third-party SaaS tools. None of them are sponsoring this or me. I'm just giving it as a alternative. Sometimes it's just easier to get something running quickly and then over time replace it with something else that's better. So I feel like Op Center is one of the best tools out there. Prometheus and Grafana are like a close second, and that's only because people haven't built all the right templates and dashboards for it. Op Center has a bunch of, Cassandra-specific metrics, basically. In tombstones, you can detect it, again, using the later versions of Cassandra, DSC or Cassandra. We can track tombstones. Actually, I take that back. You can track tombstones with CF stats in even older versions of Cassandra. It tells you when you look at the CF stats output. You can look at the systems log, Cassandra systems log. It can tell you if they're increased beyond a particular threshold. Usually it's like 1,000 tombstones. In a similar way, you can use the tools that we just mentioned. And then finally, wide partitions. Same way in the system log, you can just look for compacting large partitions or use a tool called top partitions. So when you start seeing problems, it's probably because of these 3 issues: skew, tombstones, or wide partitions. If you want to see more resources on monitoring Cassandra, DataStax, Spark, there's a link right here. When I publish the deck, you'll get it. You can also just Google it. You should be able to find it as a first result. Op Center looks like this. It can manage clusters of DSC. I believe this is Datadog, and this is Grafana. Grafana is open source. Datadog is a SaaS tool, and Ops Center is a commercial tool as part of the DataStax Enterprise Toolkit. So Cassandra Vision isn't out yet, but the two goals that we're trying to really achieve is that provide a way to visually identify Skew, like we just saw with the Excel file. And the second one, which we haven't started on at all, is to give a very simple Cassandra monitoring stack using Prometheus and Grafana. There's just too many ways to do it right now, and I'm just looking for a simple automated way of doing it. So stay tuned. I would say by the end of the month, we'll get Objective 1 done and out the door. All I'm really doing is waiting for our team to test it across every major version of Cassandra and DataStax. All right. Common Cassandra migration patterns. So before we go in deeper, are there any questions from the audience of what we just covered so far?
You mentioned something about you know, Cassandra being distributed and the data making its way across all the nodes eventually.
Mm-hmm.
How does that impact reading when there's heavy writing? Does that mean that different users will get different results if they're querying at the same time and they happen to have like a different node that they're getting their data from?
Sure, that's a really good question. I'll give you the 5,000 to 10,000 foot answer. And we can go deeper into that, you know, a little bit later in the talk. So there's tunable consistency in Cassandra, where if you have multiple data centers and you said for key space, I want this key space to be in US West and in US East. Okay, and that key space may be customer profiles, for example, right? And a person that's using the application on the West Coast is reading and writing data, but on the East Coast, somebody on the staff is pulling a report. That's exactly the use case that you're describing, right? What happens in that? Well, if the application is written to use consistency level all, which is a global all, then any write that the application makes on US West, before the application knows that it's written, Cassandra will verify that it's written to all replicas. So if it's 2 data centers and 3 replicas each, that means 6 different machines have to be saying, yeah, I got it, right? And in that case, when the person reads the data, if they say consistency level all, then that will make sure that it's getting the same consistency from all those 6 nodes. Now, that's a fairly expensive operation. Now, if you can take that expense and you can deal with 100 millisecond latency, which is 1/10 of a second, you may be fine. But 100 milliseconds in my world is like a lifetime, right? Sub millisecond or sub 5 millisecond read and writes are what I'm expecting out of an application. So the trade-off is, well, maybe I'm just okay with knowing that data is in US West. So in that case, what we would do is a local underscore all. And that would make sure that all the data replicas are consistent on US West, and eventually it'll go over to US East. There may be a little bit of inaccuracy for that information, but depending on the use, sometimes people are okay with it. So it just depends on what the goal is. If the goal is fast writes and, you know, good enough accuracy or precision on the read, people can just say consistency 1, you know?
Okay, so when you say consistency all, is that a setting on the Cassandra database, or is that a setting somewhere else? Where's that configuration?
So it's a combination of 2 things. When you create the key space and the table, sorry, when you create the key space, you say, I want to have 2 copies of this data in this data center and in this data center. So that's one aspect of it. That's a configuration of the key space. And then the consistency is defined by the client, by the application itself that is doing the read and writes. So if you say my key space has 2 replicas in each US West, US East, then when your client says consistency all, the client talks to Cassandra. Cassandra ensures that all nodes have the data, and it then tells back the client via the coordinator that everything is hunky-dory.
Okay, so if you say consistency all and there's a write by a client, and let's say it's 3 nodes. I know it's a simplistic example. Does that mean that the client is going to get 3 different responses?
Nope. Nope. I'm going to go back. I'm going to go back to the. So it's the client is always talking to a coordinator, right?
Okay.
Yeah. Coordinator is doing all the hard work, talking to the other nodes.
Okay. So the coordinator would summarize that data.
Yep.
Okay. Got it.
Yeah. So in this diagram, if you notice, right, here's a client. Here's the coordinator. The R1, R2, R3 are the 3 replicas in this data center. R4, R5, R6 are replicas in this data center. So if we did quorum all, it would talk to all of these and get that. Or if it's just a local, it would just talk to these 3 replicas. Okay?
Okay, thank you.
Any other questions before we go to the next?
Yeah, I have a question.
Sure.
What situation creates a wide partition? Is it the same as a data skew, or where there's too many values in one, or there's too many rows, or is it just a table that's too large?
Yeah, that's a really good question. So you answered part of it. It is because sometimes there are too many rows in a partition. And why does that have too many rows? Well, it's because the traffic skew caused it to have too many partitions. So that's one reason. Another is that the key is designed in a way where it doesn't matter how much traffic the whole cluster gets or what time it gets it. The data for that particular partition grows because, you know, again, it's popular is the best way I can describe it. I'll show you an example when we go to the design.
But it could be that you picked the wrong thing as a partition key.
Exactly.
Yeah.
That is generally the case. And sometimes you may have a really good design at face value, and you start with 3 nodes with 3 replicas.
Yeah.
Right? You would never see any problems. Then you add 3 more nodes, and you add 3 more nodes, and you add 3 more nodes. And eventually what you'll see is that a pattern emerges that 3 machines have more data than others for a particular table. And it's not because you designed it badly, it's just that the natural course of the data as it came in got distributed in that way. And so you have to then revisit the key design and say, how can we make it so that it's a little bit more distributed? And there's strategies to do that, and we'll talk about that.
Yeah.
Okay.
All right.
Cool. Any other questions?
Yeah, quick question on what you were mentioning about the consistency. You said the consistency is selected by the client.
Yes.
So you're talking like the client application, right? Like the
client application, yes.
So does that mean that you can select on a call by call basis? You can select this is consistency 1 versus this.
Absolutely. You can do that at a command by command level. You can say consistency all, write all this data. Consistency 1, read all this data. Right?
Okay.
So like in that case, if you said consistency, oh, write all this data, you're already sure that the data has been copied to all of the nodes, right? So immediately after that, you can say, just give me from one of them. I don't care. Cool?
Cool, thanks.
All right, I'm gonna continue on so we can cover the rest of the talk here. So the rest of the talk is about the strategy of going to Cassandra, right? And I'm just gonna give you a caveat that we're gonna be talking about software architecture here. Because moving from a relational database to a Cassandra database is not just a database shift. It's an architectural shift, right? We're talking about these things as being part of the same platform. So just be aware, we're not just gonna talk about databases from now on, we're gonna talk a little bit about software as well. And what does that mean? Well, the general trend we see is that monolithic applications that would use one big database with many different tables, going and becoming broken up into composable services. Some that have their own storage, some that are completely stateless, right? And these are just two diagrams that explain the same thing. But one thing that I like to talk about is when you think about microservices in Cassandra, I wouldn't recommend making a new cluster per service. That doesn't work, because see, Cassandra itself is built like a set of microservices. In fact, it's got 15 to 20 thread pools that are sending messages back and forth. And so when you create a table in Cassandra, it's distributed on all the nodes. And you can be pretty damn sure that it's gonna be fairly resilient, right? So the same architectural patterns apply from going from a monolithic system to a microservices system, but the thing that you have to take on faith and experience is that you don't need to make a separate database per service. You can treat Cassandra as a platform that can store multiple microservices on it in the form of a key space or a table, or maybe you can dedicate a whole data center for a particular set of services. And that's exactly what the adopters of Cassandra do. They start using it like an infrastructural service. Oh, we're gonna make a large Cassandra cluster to serve up these domains, and we're gonna make a medium-sized Cassandra cluster to serve up these domains. So if you don't know how to, this whole monolith to microservices, we're gonna talk about it in phases, but ultimately this is the major strategy that goes well with what we're gonna talk about in migrating to Cassandra. You don't have to break things into microservices, but if you do, you're gonna scale your application better, and Cassandra's gonna scale better for you. So number one way of moving data, or moving to Cassandra from relational, just lift and shift it. In some cases, you could even do the describe of a database in MySQL, and I haven't done it recently, but if it's simple enough, you can just paste it into CQLSH and it will create the table for you in that key space, okay? It works great if your partition key is already good, okay? Some people that I know will take a auto increment ID for their relational database and make an MD5 hash of it, and then they use that as their partition key. That actually spreads out pretty well. Another is that by luck, basically, your partition sizes are sane because your clustering key is well designed. And again, that's a luck factor. You have many columns, but you're not using them all. Many of them are null. That's okay in Cassandra. Another great use case is if you have content like text, JSON blobs, or just blobs of binary data that aren't too big, or XML, right? It's a lookup. Get this document, right? You can move that directly into Cassandra and not have too many issues. Where it fails is what we talked about earlier, lookup tables. If you have 100 rows in a lookup table, that's a waste of resources in Cassandra. And it just taxes the system. So why would you do that, right? There's ways to get around it. When a partition key is popular, as I was saying, it's getting more rights than other ones. And this is not necessarily related to relational lift and shift, but time series data, if you're making that time series, that time ID, the partition key, and your data doesn't come in consistency like every minute, then that's going to create some sort of skew around the cluster as well. But the big elephant in the room is, if you do a lift and shift and you start to do arbitrary queries and joins, well, join is never going to work unless you use Spark SQL. But your arbitrary query, the only way it will work is if you say allow filtering. That means you're scanning the whole cluster for that information. And that's really not the way to do Cassandra. So some things to remember here. CQL is similar, but it is not SQL. You can't query something that's not a key or is not indexed. Indexes, materialized views can have skew. And we haven't talked about materialized views, but a materialized view is basically, it's a way to get a subset of your main table and filter it on another column, essentially. Empty columns are better than null columns, because every time you put a null value, it creates a tombstone. So when you're looking at your code that's doing deletes or is using prepared statements, watch out for putting nulls in there. And since you lifted and shifted, you should do a performance test with realistic data and look at the statistics. Look at Op Center and look at Grafana to see if there's any skew. Another approach, it goes well with lift and shift in that you can't lift and shift everything. You have to eventually do normalize or consolidate. So if you have master detail objects, right, when one to many is basically, it's like one owns the many rows, you can make that into one big partition. You can also do hierarchical objects pretty well. And as long as your normalized data is not massive, 100 megabyte object is fine. Don't go beyond 100 megabytes if you're doing lots of read and writes, but if you have enough memory, 100 megabyte partition is not that big. So natural objects, when I say natural objects that can be organized into records and folders, if you have to store, let's say, orders, customer accounts, and really keep it all together, I think those objects make a really good transition. If you have many lookup tables, you can just put that into one table, right? It's a way of consolidating things. Objects that need to store history or versions. So this is one of the best use cases of Cassandra. You can keep adding or inserting new updated rows of that table and for that record, and over time let the old ones expire using TTLs. And you can do that for any object in your system. And because this is not going to add too much load, right? If you're keeping your number of rows pretty low, you can have a time travel in all your data, right? So where does it fail? Well, when your normalized data is massive, it's gonna fail because it's gonna read a very big object. A Another reason is when the standard deviation of partition size is high. It's a really fancy way of saying that some of your data is bigger than the rest of your data. And that's very possible. And we need to work around that. If you need to query on a non-key attribute or a sub-attribute, we need to find ways to get that information, maybe using an index or like a search index. Definitely not good to pull reports off of this data, right? You're not going to say select count X where this is equal to Y, right? That's not what this table is for. It's really for get me this object for this customer. Oh, and now I have everything for this customer. Get me this object for this user. Now I have everything for this user. Get me this order. I have all the order details in here. That's where you can really just go to town. And that actually makes a really good data store for REST APIs or microservices, because you're dealing with get and post, right? Read and write. Some things to remember here: Cassandra stores key values under the hood. That means you can have as many columns as you want. And you can use what I call like a region of those columns for one type of data and a region of those columns for another type of data, and essentially able to store many types of data in one table. You don't need to think about this today, but when you start to create databases or tables for analytics, sometimes for machine learning, you need to store like 1,000 columns for it to be able to churn it properly, right? That's okay. Cassandra can handle it. It's okay. Number of rows and columns don't matter. So don't worry about it. As long as it's under 100 to 200 megs. Since consolidated objects can become big, performance test with realistic data, right? This is exactly what I said here, right? Performance testing with realistic data is really a big part of doing this, because you're building a distributed platform with many, many nodes. You can't just look at one dashboard for one machine and say, oh yeah, it's fine, right? You need to look at the information for many nodes. So lift and shift kind of works, but then if you luck out, it works. If you don't luck out, you have to do this denormalization consolidation. And then it really lends its way to, well, you know what? Let's just do a microservice for a set of tables in a key space, designed like a denormalized object, right? So it works like a champ when you treat a table or a key space or a data center as a microservice domain. You design your models as if you were designing REST APIs. You design your models as if they were messages being sent in a queue. So when microservices are not waiting for other microservices, when they're non-blocking, this is great. Especially with Cassandra, you can be doing a bunch of writes and a bunch of reads. Works great. Now, when it doesn't work well is when you're trying to do too many things, meaning you're trying to touch too many tables from that one particular operation. And instead of making 100 queries from your client application, you make one query with 1,000 keys in the in clause. Okay? Not great for performance. It works, just not great for performance. And when you try to do read, write, the same operation, then you're choking up your process. It's actually better to do a bunch of writes and do a bunch of reads. So if you have to have some sequencing, it should be done outside of the microservice. It should be done in either a facade or via queue, right? And now we're talking about software, but that's the way systems are scaled. Whether you use microservices or not, ultimately, asynchronous processing is how they get done, how big systems get done. So things to remember: Cassandra itself is a set of 15 to 20 threads that pass messages through between each other, between each pool, and sometimes between nodes. So you can do as many writes as you want. It'll be fine. And when you do a read, you should do one partition per query. It's a big part of Cassandra modeling is data modeling is one partition per query means not one row per query, but rather your query returns a set of rows that happens to fit in one partition. And that's when Cassandra is most optimized. So microservices are able to be scaled yet again using a design pattern called CQRS, command query request segregation, where updates, inserts, and deletes are sent in as commands. They're then processed using an event processor asynchronously. And then all of the reads are coming from a read layer that either could be coming from the same database or from other databases. Now, why is this important for scale? Well, Cassandra, when you write data, it's writing to many, many nodes and could be many different data centers, right? So if you have a way of segregating all of your inserts, updates, and deletes, and you have a separate area of the application that it's doing reads, you can optimize a data center for reads, and you can optimize a data center for writes. They're talking to the same table. Now, sometimes people use this architecture to write data to an index simultaneously, like a search index, like Solr or Elasticsearch, while they also write it to Cassandra. In DSE, when you write data, CQRS is already kind of taken care of, because when you write data to a Cassandra table, it's automatically indexed in a search index, and then you can do a query from it. But this pattern holds well in open source Cassandra as well. Sometimes you have to replicate your information for the fastest read possible, right? If you have orders by customer, and then you have favorites by customer, and then you have past orders by customer, that's one way to put data, but then it may be orders by product, right? Favorites by product. And when you do that in Cassandra, it's okay, you can duplicate that information. But how are you going to keep track of writing that data to the same place, or to the different places at the same time? Well, this pattern, CQRS, is the way you would do that. Now, as a DBA, you don't really have control over this, except that you can design your event store and your query stores properly, so that the developers have to use that. Or you can use something like DSC, in which you can write data to a table, and because it's simultaneously being indexed, you can do queries without necessarily making a query store. So CQRS microservices, you need it when it's web scale, and that's when it performs. And you can basically drop the microphone and be like, this is how we're going to scale, right? How are we going to scale it? CQRS microservices. All updates to data are events with a payload that can be processed with command processors. So if you imagine the new tools that are out there, like containers and serverless functions, that's how they work, right? You're publishing an event, the command processor that could be written in Lambda or Azure Functions or Kubeless, which is a Kubernetes serverless function. It could take the data and it could write it into Cassandra. And they could be happening on 1 million events a second. Events are interpreted and can be used to update multiple copies of data, as we just talked about. So you can have data integrity managed by this command processor. And because the command processor can talk to any coordinator, any node in the cluster, as traffic builds up, all of the command processors are going to be able to scale. Events can be sent to and sourced from a database, cache, or queues, or directly. that's a different conversation. Like what, should we use Kafka or RabbitMQ? Should we use a Cassandra table? It's a different conversation. You can use all of those if you do it properly. But all the reads should come from query tables or report tables that are getting materialized by your command processor. When is it not web scale? Well, it's not web scale because your processors can't seem to keep up, so your queries show stale information. When does this happen? Your processors are doing too many things, so they're not picking off the items off of the queue. And so essentially, you have stale information. Not because Cassandra is slow, it's just your code is not writing it fast enough. You're doing too many events, and your queue can't handle it. So people use Redis for queues, and it fails. Or they use RabbitMQ for a queue. It scales to a certain degree, but then eventually, if you're not really picking them off, it can have a problem. Or you're constipating the queue. An event is an event. It's not meant to be a message itself, like the whole payload. So if you're putting 100 megabytes of data into a command, I would rethink that. And that happens, and so the way you deal with it is, you may upload something to S3, and then you can read it from another processor. Or you upload something to a table in Cassandra, and then you read it with the command processor for further processing. But don't choke up the processing with a big message, basically. And you didn't really segregate command and query layer, meaning if you truly separated the command and query layer, this part of the software could be technically put on a different server or a different set of servers, and it would efficiently scale differently from the command, right? That's when you know you've completely separated them out. Things to remember, well, the same things in read-write microservices as earlier. And if commands are materializing data in different places, process those in separate threads asynchronously. Meaning, data comes in, process this data here in one thread, process this data here in another thread. Don't have them compete for resources. And then you can scale the query and command processes as needed, as I mentioned earlier. All right. Any questions before we go into data modeling practices? I know I've dumped a lot of information, so, all right. So good key design. So some things not to do. Avoid using integer or long keys unless you either couple it with another composite partition key, or maybe use a hashing algorithm like MD5, and that way it'll be consistent. If you have an integer and you store the hash, the MD5 hash of that in your partition key, whenever you read data, you would have to say, take this integer, make a hash of it, and then that's what you query Cassandra with, right? Avoid using time or date based keys unless you know that data is coming in consistently, okay? And I know I said earlier you could lift and shift. You can do it, but just don't expect it to magically work, because there's times where it's not gonna work. So some things to do, more than likely UUID will work for any given table. So how do you get that information? Well, you may need to have a table, an access table, where you can say, given this key, get the UUID for X. And the MD5 functionality is basically a shortcut way of doing this. If you have to use human readable keys, use synthetic sharding, and I'll demonstrate that as well after showing it on the next slide. And as I mentioned earlier, you can combine different parts of your table to make your partition key, and maybe that's it gives it a good enough spread. Clustering keys don't spread data around the cluster. Clustering keys are about how the rows are clustered in one partition. So partition key is the first part of the primary key, and clustering key is anything after the first part. But if you have a parentheses around, let's say, 2 keys, that's a composite partition key. And then finally, and I've been saying it, to properly scale it, you got to use realistic data. You got to put realistic data in to see how it behaves. So synthetic sharding is about taking data that normally is not going to distribute no matter what fields you put into the composite key, and adding a number, 1 through 10, 1 through 100, that will then break it apart. So why will that work? Well, if you're seeing data clump up into 4 GB partitions, and you said, every time I add data, randomly assign it 1 through 10, at the very least, you're not going to have, I guess, 400 meg. Is that right? Yeah, you'd have 400 meg partitions. So sharding data, it doesn't, it was hard for me to conceive what this was about. So there's a tool that really helped me out here, and it's called the SQL Data Modeler, and I have the link in here. So imagine there's a key space, and there's a table where the partition key has user ID, product ID, time, and review ID. So in this case, user ID is the partition key, and these are clustering keys, right? So what does that look like? Well, one user ID will have 1 row here, okay? And all of these are, if I added more and more data, everything will clump up in this one user ID, right? Well, what if I added another column in here to make this a composite, right? So I clumped up, I combined user ID and product ID.
There's your partition.
So what happens now is the partition is actually stored like this. That means if more and more data comes, if it has a different product ID, it'll go into a different partition. So that will spread the data better, right? So this tool can actually create a Cassandra stress YAML, which is one of the tools that Cassandra comes with. You can play around with this on your own, but just from a pure testing, visualization perspective, I love this tool. It's open source. Actually, Seb works for DataStax, and a real sharp guy. He made this tool. You can copy and paste your schema in here and visualize it, and change the partition keys around and see what it'll end up like. Of course, it's not going to give you the diagnostics of a performance test, but at least you can visualize what your partitions are going to look like. Okay. One more way you can spread data out is maybe use the weekday if it's a time-based, right? Spread it across 6, or another one could be, use the day of the month, 1 through 30 or 1 through 31. Avoiding tombstone. So Remember when we talked about why Cassandra is fast, right? You write data. Even when you delete data, you're writing data, okay? When you set a null value, it says, hey, this column is now null. So tombstones, if you have too many of them, it has to go through all of those old records, updates, inserts, and tombstones to tell you, hey, I've got no data here, right? That only happens if the data has not already been compacted. So compaction eventually consolidates these ledger entries, basically. But until then, if you have a bunch of deletes, it's going to cause latencies, okay? My recommendation is just do a soft delete. Have a column that says deleted equal to true, okay? In your, maybe that's a clustering column, like one of the many clustering columns. So you can filter on it. And you can put a TTL value, time to live, on that row that says, you know, over the next 5 days or over the next 30 days, this data is going to be expired. So eventually in these compaction cycles, that data is going to get deleted anyways, okay? So, and the last way I would say to deal with tombstones is when you're using prepare statements, just have a processor of your prepare statements that if it sees a null in an object, to make that an empty space, or don't send it at all, okay? This is the most common problem I see, tombstones, because people are just lifting and shifting their code and they're doing many, many reads and writes. This is also why you will hear or see that, you know, Cassandra, making a queue on top of Cassandra is an anti-pattern. Because in a queue table, you would add a row and you would delete it once it's processed, right? Well, I would say you could use a Cassandra table as a queue if you don't do actual deletes, if you do soft deletes, or if you use a, you know, a pointer, like you're basically rebuilding Kafka, but you can use Cassandra as a queue if you don't actually delete. So lesson here is don't delete, don't add nulls if you can help it. Try to use soft deletes, try to use TTLs, and let Cassandra do its housekeeping later on. All right. Now that is the end of this talk. We talked about core concepts in Cassandra. We talked about how to detect issues as you're migrating data into Cassandra. We talked about generally how people are moving data in and how that relates to software architecture. And then we talked a bit about the best practices on data modeling. So any questions? Go ahead.
Yeah, I had a question. You were talking about synthetic sharding, and in terms of your primary keys or your partition keys, is it possible to have too many columns in it, or can you go as big as you want?
You're talking about in your partition key or in your primary key?
Actually, either.
Either. Okay.
I'm wondering, are there some issues with that though?
So let me show you what it ends up happening, right?
Yeah.
So let's say I put everything in the partition key here. All right. That means I have to manage for every one of these. I have to manage a new partition key, and I have to have a different hash for this, and I have to replicate it. So
I'm going to have
sparse
exactly
what you want. Okay, it may be exactly what you want, but just remember that the replication happens at this level, at the partition level.
So right? I'm creating a new partition every time I'm going to create too many partitions.
You can have a lot of partitions. That's not the problem. You can have as many partitions as you want. I'm just saying that that's what's happening under the hood. So in terms of what happens if you add too many things, I don't know. I haven't really made any crazy tables where I have like, 50 items in the primary key.
Yeah, I mean, it seems like it would avoid the problem of getting like a partition that's got too much, like a skewed partition.
Sure. So that's a good point. And so really what it comes down to is, do you know all of these things? If you don't know all of these things, then you can't query it. Right? So that's part of the partition key design, is that we're assuming that you at least know the partition key. You don't have to know all of the clustering keys. That's an optional. But you definitely have to have the partition key.
Yeah.
Right? And if it's a shard ID, right, we're talking about, okay, well, you know what, I really want it to be, I'm only going to have user ID and product ID. Right? And I'm not going to know the time, and I'm not going to know the review ID, and I'm not going to know the profile name, but I want it to cluster and order the data in that way. So, what does sharding it mean? Well, sharding it means that, I don't know why this is a little unresponsive right now. Sharding it means that, let's let it wait a little bit. Sharding it means that when I add new entries for user ID and product ID and all of these things, I'm just going to increment 1 through 10. And when I read it, I would say, select star from this table where user ID is equal to this, product ID is equal to this, and shard ID is equal to 1 and 2 and 3, meaning like I could put an in statement, but obviously we talked about, we don't want to do an in statement if it's like 100, but, or we could just say, you could do 10 queries on your client application. And that is more performant. You're basically coalescing those rows on the client side, but that's fine. It's fine because you sharded it, it technically is on a different partition. So get it from a different computer, right? Get it from 10 different nodes if that's how it's spread around the cluster, right?
Yeah.
Cool. All right, it's not liking me, so I'm just gonna quit the page here. I think I must have put some bug in there. I'll have to talk to Seb about fixing it. Any other questions about what we covered today? So there are a couple of resources I wanted to point you guys to. Cassandra.Link is a site that we, at Anant, we publish it. It's searchable. It aggregates blog entries from most of the credible Cassandra blogs out there by data stacks, by other practitioners of Cassandra, including us. And we curate a lot of great knowledge out on the internet that we know is credible and good. So you can find that on Awesome Cassandra, which is a GitHub page. But we also index that inside Cassandra.Link. This tool that I showed you guys is also here. Cassandra Data Modeler by Seb. There's a great deck by Jeff Carpenter. Jeff Carpenter, who works at DataStax, has written a book on Cassandra, The Definitive Guide. That's Jeff Carpenter. Has a really good deck on how to do data modeling for microservices with Cassandra and Spark. One of the blog posts that we've written that's pretty popular on Google these days, but common problems in Cassandra data modeling. It actually has many references to other great articles about data modeling, so it's a good primer survey. And then for monitoring Cassandra and Spark, either using Ops Center, Prometheus, Grafana, lots of great references here. And if you guys want to stay in touch, just subscribe to the mailing list, and you'll get a weekly update. We're hiring, we're partnering. We are definitely a growing team, so If you happen to know anybody that is looking for work in the type of things we work on, you know, please let them know, and they can just go to the Anant.us site and fill out the Join Us form. Well, that's it for today, guys. Hope everything was good. You guys learned something. Please reach out to me if you have any questions. My email address is just Rahul, R-A-H-U-L, at Anant, A-N-A-N-T.us, and I will try to get back to you as soon as I can.